Hey, I'm here in LTSpice. What I'm going to do in here is mostly Ohm's law, but it's the impression I wanted to make was of the setting that this circuit exists in. I have over here 12-volt supply supplying the circuit, and over here I've got another supply, but this is just instead of an oscillator. This is a square wave pulsing between 0 and 12 volts at the sort of rate that you'd expect for something like 9600 board. That's feeding into a BC547 transistor. That's like a 2N2222. If you're not familiar with a BC547 NPN transistor, that's at the collector being pulled up to 12 volts through a 2.2K resistor, and we're more or less saturating the base there, so it'll effectively be pulling to 0 volts there. Don't worry too much about the 50 picofarad capacitor. I just put that in there to knock the tops off the pulses, the ringing off the top of the pulses. And here I'm trying to simulate some cable lengths. I've got positive feed coming through this wire here, and then through, I'm saying that R3 is representing kind of a system load, and coming back through the return on R2. And so I'm saying, 50 to 100 meters of some certain type of cable might be, you might see that as 0.5 ohms worth of resistance on this runner wire here and this runner wire here. This wire here, where the signal is coming through, I'm suggesting that there wasn't as much copper needed to get the signal out to here, so less different wire, less resistance. Excuse me, it can have more resistance because the load isn't so much on the end of this. R4, I'm suggesting, is 12K resistance input into some silicon receiver for that signal. I think 12K is not too ridiculous for that. Having a look at R3 here, which I've said is I'm representing as the load. So on this side of the cable, we've got 120 milliamps going through here. So the voltage drop on this wire here, the positive positive voltage feed, is also 120 milliamps. Sorry, the voltage drop is going to be half 120 milliamps, so it's going to be 0.06 volts. And that's going to be the same for down here. Now, what I want to look at is what happens at this junction here, and I want to make most of my measurements on this end of the cable. So if this was some silicon receiver, you'd be measuring the input with reference to its ground, which is going to be at this end of the cable. So I'm just going to move that reference to up here so we get correct measurements. Okay, I'll just run that, and so we're still looking at this point here, and we're more or less around the 0 volt mark. But let's see what happens if I decrease the resistance, therefore increasing the load. And it's come down a little bit there. I'll just decrease the resistance again of the load. Coming down now to 0.2 volts. I'll bring that down to 10. And we're kind of 0.5-ish there. I'll bring it now down to 5 ohms, so we've in our imaginary load we've got a bunch of light bulbs turned on. And this is where I'm suggesting this can start to become a problem. We're now down to about minus 1 volt at the bottom of this these pulses. I'm not too worried about what's happening with the positive side of these pulses. I'm suggesting that in that silicon receiver there'll be thresholds, let's say somewhere between 7 and 8 volts, 6 and 8 volts for one going logic, and some threshold down here around 1 to 3 volts for negative going logic, and 0 logic rather. But then it's the actual voltage going negative here that I think in some cases could be a problem for the silicon the receiver. So I'm not suggesting this is a very typical scenario. I'm just saying this is something that you might come across. I have, and something to look out for anyway, something to consider when. And it may not even be in this kind of scenario where it's on the end of a cable. This could happen on a circuit board by itself. It's possible. Okay. Having a look at how much current's going through that positive feed, we've got 2 amps there. So we've now got a volt dropped across this length of cable, and we've also got a volt dropped across this length of cable here. Now, you have to remember, and that's more or less the volt that we're seeing here, you have to remember that this signal here is being generated from over here, and as I said, I'm not sort of worrying about the positive side of things, so forget for a moment that it's being pulled up to 12 volts. Let's just consider what happens when the transistor is turned on and it's pulling down to ground. The voltage that we're measuring here from this reference here, this R4, the input into the silicon, doesn't represent a big load, so there's not a lot of current being pulled, and we can have a look at that. There's not a lot of current being pulled through this wire here to the silicon receiver, so there's not a big voltage drop across this wire for the signal. And when if we can imagine at this end having a multimeter and putting your common probe here and voltage input probe here, it's because I'm saying there's not a lot of voltage drop happening through there or through the junction of the transistor, I'm saying that it's effectively the same as putting a multimeter here and common here and measuring back across this cable, if you could do that, if that was practical. But in a circuit analysis way, if you think about it that way, and in fact, just to really try to illustrate that, I might get rid of a couple of components here. Just bring it back onto that. So I'm just going to get rid of that 2K2, and I'll get rid of the 50 picofarad. And I'll just get rid of that there. Remember, I'm saying, let's imagine that transistor is on, and I'm saying that because we're saturating, there's really not a lot of resistance there to really consider. And there's only 3 ohms. I might leave that there, but you can start to think that it's like 0 ohms. So I'll just run that again. Just clean that up a little bit. So we know that there's a volt being dropped across here, and normally in simple circuit analysis, you'd put your common probe at the supply 0 volts, and then measure about the place to see all the voltage drops. So thinking that way, you can start to see, well, if I put my common probe this way and measure back the other way, you'll start to see, you'll be measuring those voltage drops in the negative. So that's what we're seeing there. And in fact, because there's that 12K there, looking at this really, you might as well not even consider that the 12K is even there, and because that's 3 ohms, it might as well be nothing. And so it's really like just measuring between here and here, if that makes any sense, as if between here and there was a short circuit, more or less. So that's why you end up seeing -1 volts when you're pulling a lot of current through that load, and you end up with a voltage drop here. And that's only happening because we've got that, we're using that as the common return for both these light bulbs and the signal. Alright, I'll just try to, now that I've completely ruined the circuit, I'll just try to quickly rebuild that, if you can bear with me for just a moment. So we had that, we had a 2K2 this way, and hook it all back up. So the next question is, you've got this problem. It is possible, depending on what that silicon receiver is, if it's not tolerant of those negative voltages, you can have some funny stuff happening. Maybe you'll kill the input to your chip. Probably not. What's more likely to happen is that whatever it's doing with it, or how it's going to produce an output, could be unpredictable. Let's see, are we just about... No, got to give that a value. And we haven't picked transistor, just go... Oh, 2N52 is there. Well, we'll just leave it on that. That's good enough. I've forgotten the 2K2. Okay. Back to normal. Alright, the next thing then is we can clamp that negative voltage by putting a diode in this orientation, because you remember when we're measuring here and looking at this point here, we're seeing negative. So when that happens, that one volt can get clamped by this diode, and we want to choose something with a low forward voltage, like some sort of Schottky. 1N5819 is going to be overkill, but it's, for illustrating the purpose, it's not so bad. There we go. Just zoom in on that a little bit more. Okay, so we're back down to 0.3 volts or so, and that is what you can do to overcome that kind of deal if you ever come across this sort of problem. Thanks for watching. See you next time.